The United States recently deployed a low-cost strike drone over Iran that immediately triggered concern across Russian military analytical communities worldwide. This system is not hypersonic, stealth, nuclear-capable, or particularly fast, yet its communications architecture makes it strategically disruptive on modern battlefields. The drone is called LUCAS, meaning Low-Cost Uncrewed Combat Attack System, developed by American defense contractor SpectraWorks to reshape attritable strike doctrine globally. Unlike expensive cruise missiles, LUCAS represents a scalable precision strike platform designed for saturation warfare environments where cost efficiency determines operational sustainability. Russia's concern does not come from the drone's airframe propulsion, payload capacity, or aerodynamic performance, which remain broadly comparable to Iranian Shahed series loitering munitions. Instead, the alarm originates from its communications backbone, believed to rely on Starlink-derived satellite mesh connectivity resistant to conventional electronic warfare suppression techniques. Electronic warfare dominates drone survivability across Ukraine's front lines, where signal jamming determines whether unmanned platforms reach targets or crash before completing strike missions. Traditional loitering munitions depend heavily on GPS navigation signals transmitted from medium Earth orbit satellites thousands of kilometers above the battlefield environment. These navigation signals arrive weak at receivers, allowing truck-mounted jamming systems to overpower them with relatively modest electromagnetic transmission strength under combat conditions. Russia successfully exploited this vulnerability, using systems like Zhetel, Krasuka, and Lear series jammers to disrupt Ukrainian drone navigation across contested operational sectors repeatedly. However, Starlink-based guidance introduces an entirely different signal geometry that fundamentally complicates suppression attempts through localized electromagnetic interference operations. Starlink satellites orbit much closer to Earth than navigation satellites, producing stronger signals that remain significantly harder to overwhelm using mobile battlefield jamming platforms. More importantly, Starlink operates as a moving mesh constellation rather than a single vector transmission source, eliminating predictable interference targeting opportunities for adversaries. Each terminal constantly switches between satellites overhead, meaning disruption requires simultaneous suppression across multiple dynamically shifting communication pathways during flight operations. This creates a technical challenge far exceeding conventional anti-GPS electronic warfare tactics previously sufficient against most loitering munitions deployed in Ukraine's conflict zones. As a result, Russia would require a dramatically expanded electronic warfare infrastructure to replicate earlier successes against navigation-dependent unmanned strike platforms used by Ukrainian forces. Chinese military simulations examining Starlink suppression scenarios over Taiwan suggested hundreds of airborne jammers would be required for partial communications denial coverage effectiveness. Lower-powered suppression alternatives would require thousands of coordinated electronic warfare drones operating simultaneously to disrupt satellite connectivity across contested operational environments effectively. Applying similar calculations across Ukraine's extended front line suggests Russia would need thousands of synchronized jamming systems deployed continuously across large geographic operational sectors. Such infrastructure expansion would impose enormous logistical burdens on already strained Russian electronic warfare production, deployment, and survivability capabilities under Ukrainian counter-strike pressure conditions. Electronic warfare vehicles emit detectable signals that frequently expose their locations, making them vulnerable targets for artillery, drones, and precision-guided strike systems during engagements. Independent battlefield verification sources confirmed dozens of Russian jamming systems destroyed since 2022, highlighting the fragility of suppression networks under persistent reconnaissance strike pressure cycles. This vulnerability complicates any attempt to build large-scale suppression grids capable of neutralizing satellite mesh-guided strike drones entering defended operational airspace from multiple approach vectors. If LUCAS platforms integrate Starshield communications rather than civilian Starlink architecture, disruption becomes even more difficult due to enhanced encryption and military-grade authentication protocols. Starshield operates partially through satellites controlled directly by the United States government, reducing vulnerability to commercial access manipulation or adversary exploitation attempts significantly. Such architecture transforms inexpensive loitering munitions into persistent networked strike assets, capable of maintaining real-time communications across continental-scale operational environments without interruption. Risks. This enables dynamic retargeting capabilities previously limited primarily to high-end cruise missiles or aircraft supported by sophisticated command and control infrastructure networks. In practical terms, connectivity becomes more important than payload weight, range, or speed in determining strike effectiveness during modern distributed precision warfare scenarios. A drone capable of receiving continuous satellite updates until final impact can adapt mid-flight, improving survivability against countermeasures and increasing terminal strike accuracy substantially. Russian military analysts increasingly recognize this shift represents a structural transformation rather than incremental improvement in unmanned strike platform design philosophy worldwide. The true threat emerges when such communications architectures extend beyond LUCAS into cruise missiles, artillery rockets, naval drones, and autonomous reconnaissance strike swarms simultaneously. If integrated widely, satellite mesh connectivity could enable precision strike systems to operate globally with persistent guidance independent of local navigation infrastructure availability limitations. This would reduce the effectiveness of traditional electronic warfare suppression doctrines built around disrupting predictable satellite navigation dependencies across contested battlespace environments historically. Russian planners therefore face a dilemma, requiring either massive investment in anti-satellite suppression technologies or development of equivalent domestic orbital communications constellations rapidly. Russia's Zorky satellite constellation project represents an early attempt to replicate Western low-orbit communications networks supporting future unmanned warfare operational resilience requirements. However, projected deployment numbers remain far below Starlink's scale, limiting near-term effectiveness against constellation-based communications advantages currently enjoyed by United States forces globally. China is pursuing a parallel strategy through several competing satellite constellation programs intended to provide redundancy against Western orbital communications dominant scenarios. Projects including Qianfan, Guowang, and Honghu demonstrate recognition that future battlefield superiority depends increasingly on orbital infrastructure rather than purely terrestrial weapons development priorities. Meanwhile, anti-satellite weapon concepts remain operationally limited against constellations numbering thousands rather than hundreds of individual orbital communication nodes distributed globally. Destroying enough satellites to meaningfully degrade Starlink coverage would require sustained launches, repeated engagements, and significant escalation risks extending beyond regional conflict frameworks. Consequently, the emergence of LUCAS signals not merely a new drone platform, but an early indicator of network-centric, attritable precision strike warfare expansion globally. Cheap, unmanned platforms linked to resilient satellite communication meshes represent a scalable model capable of reshaping strike economics across future high-intensity conflict environments dramatically. That shift explains why Russian analysts increasingly describe satellite-guided loitering munitions not as tactical tools, but as strategic disruptors of traditional electronic warfare dominance assumptions. What makes LUCAS strategically important is not its individual performance, but the doctrine it represents for future distributed precision strike warfare environments. Modern conflicts increasingly reward systems that combine affordability, connectivity, and scalability, rather than relying exclusively on expensive, high-end platforms with limited deployment numbers. Satellite mesh connectivity allows even expendable drones to function as intelligent network nodes instead of disposable single-use strike tools with restricted autonomy. This transformation reduces the effectiveness of traditional electronic warfare strategies that previously dominated unmanned battlefield survivability calculations across contested operational theaters worldwide. Russia's concern, therefore, reflects recognition that communications infrastructure in orbit now determines battlefield precision advantages more decisively than platform sophistication alone. If replicated across wider missile and drone inventories, this architecture could permanently shift the balance between offense and electronic defense in high-intensity conflicts. Future wars will likely be decided not only by weapons themselves, but by which side controls resilient global satellite communications networks supporting them. In that sense, LUCAS should be understood not as a weapon breakthrough, but as an early signal of a deeper military transformation already underway.